simple overview. Chemistry, the whole field of chemistry, everything that we've been looking at, really boils down just to two things, or one thing really. The study of any two atoms interacting with each other. Depending on that interaction, we then classify it or come up with some other type of term. We can then scale and apply that term to larger and larger things, come up with conversion factors and all sorts of other fun things that add out of that. But ultimately, all it is the interaction of two atoms and what they can do. Right? So as certain aspects, first off, what makes the atom? How do we make an individual atom? How is an atom built then, if you don't want to say we make it? We have a nucleus. What's in the nucleus? Protons and neutrons. Right? What's outside the nucleus? An electron cloud. So we have protons, neutrons, and electrons. So we could switch this up and say that chemistry is not the study of any two atoms, it's the study of any two subatomic particles. Protons, neutrons, and electrons interacting with each other. Okay? Would I ever put a proton near another proton? Why not? Opposite charge repulsion. Okay, so there's one of our first studies. We would never expect multiple protons near each other. But
you mean same charge repulse? You said opposite charge.
Same charge repulse. Yes, thank you. Okay. But when we move up to helium, how many protons do we have? Two. How can we now have two protons near each other? We bring in our third subatomic particle, our neutrons, to neutralize that repulsive force of that same charge repulsion. Right? What else do we introduce? When we look at the helium atom, is it just protons? There's also electrons. Why are there electrons? To balance out the charge. We have these positively charged particles. Charge is inherently bad, so we neutralize that charge by bringing in a negatively charged particle. We have now built an atom. What happens when I take this atom with its protons and its electrons and I bring it near another atom?
Nothing.
What does that other atom have?
Protons,
Neutrons, and electrons. How do those particles now interact with each other? If they interact strongly, hey, now we're maybe looking at a bond. If they interact weakly, we don't have a bond. So all we're doing is scaling upwards from just those two subatomic particles. All the calculations that come out of it are just quantifying this, coming up with some way that we can count and manipulate these variables. Okay? So when we evaluate a molecule, or really any of our two atoms, what is the most likely part of that atom to interact with the other one? Our electrons. So it's now the electrons from one atom seeing the nucleus of the other and starting to be shared back and forth between. And we now have some type of interaction. Okay? Would we expect the same type of interaction depending or with different atoms? So if I now switch that from being carbon to fluorine, would I expect the same type of electron sharing happening between hydrogen and carbon versus fluorine and carbon? Or fluorine and hydrogen?
Yes and no.
Okay. Yes and no, we're still getting the electron sharing, but is it sharing as much? Okay. There's going to be a slight variation to that. And that's ultimately all chemistry is doing, is trying to quantify that variation to some extent. Okay. We can do this or scale this up to a larger system, okay, that in theory we're somewhat familiar with. We can take two people. Okay. These happen to be two happy people. And we're concerned about how they potentially interact with each other. At this point, they're too far away to do any kind of interaction. So we don't expect anything. We don't predict anything. But what happens if one starts making googly eyes at the other? We start to build some kind of attractive force between these. Okay. What happens if that attractive force becomes greater? Maybe now they have a couple. They're not dating, they're actually a couple now. What if that gets even stronger? Have a wedding. Right? What happens if we now go through and say that there's a different person that comes along? Okay? That different person can now potentially destroy this relationship. Okay? Maybe one of them dies and falls off. Okay? Chemistry is just looking at those interpersonal relationships. It's the same thing, just down on a very minute scale. So what we're trying to do is come up with some ways to quantify these. Right? So we've looked at bonds. Okay? Our bonds are effectively the type of weddings that we have. Okay? You've got, what is it, by law wedding, because you've been living with each other for 10, 15 years, so you're by definition married. Okay? There's also the, I just turned 18, I hate my parents, so I'm going to get married. Okay? There's also the, we really like each other, so now we're going to get married. We have different tiers of what's happening within these, and we get different levels of that type of interaction. I was drunk in Vegas and got married. We got different types of interactions between these. Okay? So it's the same thing as happening now with our bonds. So we can look at that attractive force in our bonds, in ionic, polar covalent, and covalent. Well, how did we classify these? What happened in an ionic bond?
Difference in charge?
Okay, we end up with charges. How do we get charges, though?
Because the metals are less electronegative than the non-metals.
Okay, we have a difference in electronegativity. Way to give me a really long word.
You're welcome. That's for you.
I appreciate it. Okay, we have a large difference in electronegativity that's giving us that ionic thing. Ultimately, to get those charges, what has to happen?
Electrons have to be shared.
Close. Electrons are not being shared, technically, in the ionic bond. They are being
Taken.
transferred. So we have a transfer of electrons from one atom to the other. So if we take a sodium atom near a chlorine atom, the sodium atom gives up its electron to the chlorine atom to give us sodium ion and chloride ion. So we have a transfer of electrons. Okay, what happens if we look to the extreme? We look at the opposite of that, a covalent bond. Do we have any of these charges? No. Do we have a difference in electronegativity? No. Okay, no difference in electronegativity. I'm abbreviating now. Okay. Do we get a transfer of electrons?
No.
What do we get instead of a transfer of electrons? We have a sharing of electrons. Okay, so we've come up with ways to kind of classify these differences. What happens in the polar covalent situation?
Very minute changes in charge.
Okay. This has some subtle combination of both.
Partial charge? Yeah.
This is where we end up with partial charges. Okay, and all of these kind of rules are fine and dandy, except we need to come up with some way to predict. Well, we've got the periodic table that we can use. We can come up with ways that we can classify each of these types of bonds. How do we classify our ionic bond? What type of bond do you have here? Sodium and chloride, that is a metal and a non-metal, which makes it what type of bond? Ionic. So we've come up with a rule of thumb to look for a metal and a non-metal. Okay. That was our big rule on being able to classify the ionic bond. Okay. Is that going to become important? Incredibly important. That's the next slide. How do I know, or what type of bond do I have between carbon and carbon?
Covalent.
How do I know it's a covalent bond?
It's the same thing.
It's the same atoms. Okay, so to classify our covalent bond, we have same atom to the same atom type.
Plus the color.
Can't ever call me not color codey. Yeah, that's a description. Okay. What else? Because it's not just carbon to carbon. I could do fluorine to fluorine, but that classifies under the same atom to same atom. What was our other one?
Carbon and hydrogen.
And carbon to hydrogen. Those are our classifications for our covalent bond. So a real quick examination of the structure of the atoms that are connected, we can now start to predict something about the bond characteristics. What do we do for our polar covalent? What type of bond do we have between oxygen and hydrogen? Polar covalent. How do you know it's polar covalent? Now you can cheat and just jump to the color coding, but I stole that answer from you now.
Because
What's
they're
that?
both non-small.
What do you mean the name? I'm actually not sure what you're talking about, so that's why I'm asking. I really don't know what where you're trying to go with. So if it's a nonmetal and a nonmetal, okay, that classifies it under the covalent bonding rule. But we have two types of covalent bonds, polar covalent and nonpolar covalent. Okay. So OH is a covalent type bond, but what makes it polar covalent as opposed to nonpolar covalent, or the lazy way of just calling it covalent? What's that difference?
Oxygen is more electronegative than hydrogen.
True, oxygen is more electronegative than hydrogen, so I have a big difference in electronegativity. Why is it not an ionic bond?
Because they're both nonmetals.
Okay. They're both nonmetals. So this type of bond has characteristics of both the ionic bond and the nonpolar covalent bond. We're looking at a large difference in electronegativity, but on nonmetals. Okay? That's a really dangerous definition in my opinion. Okay? A lot of different things you have to look at. I would switch it up, and I would change this out to it's not ionic and not nonpolar covalent. So I'm asking you to memorize two things. Definition for ionic bonds, definition for covalent bonds. If it's not one of those, it's polar covalent. Does it work perfectly? No. Right? Does it work for the most part? It works pretty darn close to everything you would ever need.
We don't look at metallic bonds.
And I'm intentionally leaving metallic bonds out because it's not worth talking about in this class.
Talk about bronze.
No. Okay. So what do we do with this information? We talked about this a long time ago, all of what the bonds are. What can we do with these bonds? Okay. Well, what happens when I now take, say, that hydrogen atom on that OH and I bring it near, I don't know, the chlorine of the sodium chloride? We're now looking at two new atoms, the hydrogen and the chlorine. I want to be able to predict what's going to happen between those. I want to have some understanding of what interactions can potentially come out of that. And because they aren't physically bound to each other, these rules don't work. I need a different set of rules. Those rules are now going to be looking at the intermolecular attractions. Notice all of our bonds are intramolecular. It's within a molecule. Now what we're going to be concerned about is taking two atoms that are now in separate molecules and bringing those two atoms near each other. What happens with their interaction? Okay, this should have stepwise a little bit nicer, but oh well. Let's focus in the upper left-hand corner. We'll erase all that fun stuff. Actually, I changed my mind. I'm not going to erase that. I'm taking now my molecule of sodium chloride, and I want to know how it's going to interact with another molecule. In this case, I'm picking another molecule of sodium chloride. I'm trying to maintain it because I'm trying to reduce variables, make it as simple as possible to do this comparison. Which interaction is more favorable? Top or bottom? Ooh. You guys just did a very advanced chemical question, or answered a very advanced chemical question, believe it or not. Why is the top the better interaction? No, it does not have to do with the same thing.
Is the distribution of electrons on the molecule oriented towards one side or the other?
Remember, what happens when we have an ionic bond? We generate charges. There's a transfer of electrons. Those electrons go from the lower electronegative element to the higher electronegative element. Which element is more electronegative? Chlorine, which means chlorine takes those electrons. If it takes those electrons, what happens to it? Okay. It gained electrons, so it should become negatively charged. We could start to evaluate size. I don't even want to bring size into it, and it's not that it's getting smaller, it's going to have to get bigger because you've added electrons to it.
But isn't the cloud shrink because it's more electric?
Not on ions. What happens to the sodium? Lost electrons. So now its charge is?
It was oxidized.
Fair enough. The atom loses electrons, it becomes? Positive. New question, entirely new question. What charges build in this molecule?
Neutral.
What charge does the sodium become? What charge does the chloride become? It's kind of being sarcastic with entirely new question. Go ahead.
Sodium is positive and chlorine is negative
Why?
because it's the same.
It's the same system. Chloride is still more electronegative than sodium, period. It always is. Chloride will always take the electrons away from the sodium. So the chloride will always become negatively charged. The sodium will always become positively charged. Freaky question. Now what happens? What do you mean same thing? Negative charge showed up on the left, positive charge showed up on the right? No. What changed?
You have to associate them with the actual atom.
We're associating the charge with the atom that's more electronegative. In this case, I just swapped the order of them. Chloride is still more electronegative than sodium. It is still going to take those electrons away. Sodium is going to be left there.
Not the metal was supposed to come first, though.
Metals in a formula are always supposed to come first. But when you go up and talk to a person, okay, you may talk to them face to face. What if their back is turned? Okay. Would you still potentially talk to them? So if my back is turned, you would never say anything to me.
Put a kick me sign on you.
Okay. We can interact with people. We can interact with molecules from every which angle. Why do we only give you this metal first, non-metal second?
It's not meant to represent the structure.
Because what we're trying to do is ignore structure. We're only looking at the formulas. As soon as you move into interactions, can you interact with somebody that's behind you?
Yes.
Yes. You can interact with somebody every which direction. Okay? Molecules can do the exact same thing. So what we're looking at here is not we have to fit this formula. What we're looking at here is the molecule is now turned around. Okay? Because I can pick that molecule up and I can turn it over. Okay? In this situation, which of those interactions would I expect to be the stronger attractive force? Why the opposite signs?
Because some different charges affect.
Opposite charges attract, same charges repel. How do we know same charges repel?
Because magnets.
We can go back to magnets. North and north end of a magnet repel each other. North and south attract. We can go back to the structure of helium. When we put in 2 protons, why is our mass not just 2 to account for each of those protons?
We need neutrons.
We had to add neutrons. Why do we have to add neutrons? To keep those positive charges close enough to each other, to overcome that repulsive force. Okay? So what we've got in this situation now is a favorable interaction in that top one. The bottom one is not a favorable interaction. Said another way, in that top case, we neutralize the positive with the negative. In the bottom case, we end up adding more negative. Okay? Which would you rather be shocked by, the electrical outlet or a 9-volt battery? Probably the 9-volt. Why? Less charge.
So are these two going to become linked to each other then? And if so, are they going to continually get linked with new ones? Or structured ones?
So then what we could do is start to predict something about how this molecule would interact with other molecules in the bulk phase. If we were in the bulk phase, would I expect those to continue to link outwards? Yeah, because at each end I've got a positive and a negative. What do I want to do? Neutralize that positive and negative. So what do I do? Put another positive or another negative on either end to balance that out. And I end up with a very regular structure, which for salt, what do we end with? What phase do we get?
Solid.
A solid. Why? Because there's a very strong attractive force between the molecules. That strong attractive force must be overcome to get us up into the liquid or into the gas phase. Okay? So just by understanding the minimal interactions, we can start to predict something about phases. You want to try another one? You don't really have a choice, just so you know. Bottom case. Which interaction is our favorite one? Top or bottom? I only heard 4 voices. I want to hear a few more voices in this. What do you think? Top or bottom? Heard a little bit more there, and I'm hearing a little bit of a mix. There's a reason there's a little bit of a mix in this one. Okay. Why might there be a mix of possible answers in here? What we want to go through and do is the exact same process we just did with the sodium and the chloride. What type of bond do we have between carbon and hydrogen? A nonpolar covalent bond. What charge builds on each of those atoms? No charge, so silence is kind of a good answer there. No charge builds on either of those atoms. If there is no charge, does it matter which of these interactions lines up? No. There is no way to force one interaction over the other. Both of those are equally likely. That's probably the hardest one. What happens with OH? Which interaction is favored? Top or bottom? We're getting a mix on this one. Okay, so let's address the mix. We're looking at a polar covalent bond. How do we know it's polar covalent?
Because it's not ionic.
It's not ionic, and it's not nonpolar covalent, because that did not match the definitions we just outlined. Where do the electrons spend most of their time? Take a look at that bond. Those electrons are going to move towards the oxygen. Why the oxygen?
It's more electronegative.
Oxygen is more electronegative. So let's push this to the extreme. Let's just say oxygen takes those electrons. What charge does it become?
Negative. Something.
Gained electrons, so it's negative. What charge does the hydrogen become? Positive, because it lost electrons. Okay. This starts to look an awful lot like what we drew for our ionic situation. Okay. So if we're going to draw it the exact same, that would suggest that it is the exact same bond. Is it the same bond?
No.
No. We have to add something to this structure to make sure that it is different from the ionic situation. What we're talking about is not a complete transfer of electrons, but only a partial transfer of electrons, which means that oxygen doesn't become completely negative, it becomes partially negative. What was our mathematics symbol for partially?
Lowercase delta.
Our lowercase delta symbol. That should look really familiar, particularly for those of you that have retaken the show your work part of the exam. Whole new, entirely different question. What happens with the other OH?
Hydroxide.
What happens to that oxygen and that hydrogen? Okay, we're looking at the attraction of the electrons between the oxygen and the hydrogen. Where do those electrons spend most of their time?
In the middle.
Okay. So, sorry, but I'm going to have to veto you now. Where do the electrons spend most of their time?
Oh. Hydrogen.
I said veto you. You're done. Yeah.
I'm not allowed to.
Yeah, sorry. Not because you were wrong, or necessarily because you were right, but nobody else is participating. So the rest of the class can't use you as a crutch anymore. Where do the electrons spend most of their time?
The oxygen.
Why should the electrons spend most of their time on the oxygen?
It's more electron.
The oxygen is more electronegative than the hydrogen. How do you know that? So some people are looking at the periodic table. That's a good place to look. Okay? We know oxygen is more electronegative than hydrogen because someone way smarter than all of us went through and calculated electronegativities and tabulated it for the periodic table. And what we learned was that there's a nice periodic trend. And that trend says that for electronegativity, where's our most electronegative element? The upper right corner. Fluorine is our most electronegative. And our least electronegative? The lower left. Which is closer to fluorine, oxygen or hydrogen? Oxygen, which means oxygen is more electronegative. What does that mean it does to the electrons in that bond? Goes to the oxygen. Oxygen has now accepted electrons. What charge does it become? Becomes negative because it's gained electrons. This is a polar covalent bond. We cannot call this or label this as an ionic bond. So what do we have to do? Partial charge. What happens to the hydrogen? Partially charged positive. What happens in the bottom case? Just underneath that. Partially charged positive on the hydrogen and partially charged negative on the oxygen. Which interaction between these two is the favored interaction? The top one is favored. Why? There it is. Say it again. It neutralizes the charge. Everything we are doing is trying to neutralize that charge. In our ionic situation, we looked at the top interaction to neutralize that charge. In the bottom situation, we had no favoring. Why was there no favorites? Because we already started neutral. If you're already neutral, there is no reason to favor anything. Okay? Yes?
Is there a type of bond where the electrons can be treated more freely and they will be able to move to whichever side was
Metallic. Yeah. Electrons can move differently in different systems. That would be saved for a different class and different properties. Okay. So we've got all of this now labeled information up here. We're going to take this a step further. What type of bond was shown in sodium chloride? You can participate again. It's okay. What type of bond was shown between carbon and hydrogen? Our nonpolar covalent. What type of bond was shown in OH? Polar covalent. Those were exact electrons sharing between those atoms, okay, or transferring. What we've now gone through and done is we've shown a bunch of dashed lines. Okay? Those dashed lines aren't a formal sharing of electrons anymore. Those are some type of other interaction. Okay? So what we now want to do is look at that other interaction and see if they're different from system to system. So let's take a look at our top case. We'll call this one A and compare it to case B. Are they different? Yes. Good. They are different. In one case, we have a negative to a positive. The other case is neutral to neutral. So there's definitely a difference. Give me more than that.
One trades electrons while the other shares or transfers electrons.
That's looking at the bonds. There is no bond. You're looking at dotted lines in between these. So we can't look at a transfer or a sharing of electrons because that is not happening. There's a large difference of electronegativity up in the ionic one. What is that doing to that interaction?
is it more potential energy?
Okay. We can look at it as an energetic. Puts more potential energy in it. Okay. Take it a little bit further than that. Okay. If we were going to compare people, how could we rank people within the classroom? It doesn't really make sense to rank based on brown versus white hair. Okay. How could we rank people?
Age.
Okay. Height and age, I mean, those kind of work, but those aren't super ranking things. You go to the Olympics, you don't go to the Olympics and say, ha, you're 70, you get a gold medal. Okay. Congratulations for surviving. Okay. So when we go through and rank and we do competitions, what are we evaluating? Some skill level, typically what comes with that skill level in a lot of those cases. Physical aptitude, right? A strength. Is there a difference in strength between these interactions?
Yes.
Oh yeah. What is that difference? Why is there a difference?
One should be repelling because it's the same.
A and B, there's no repelling because there is no same charge here. Okay, we just have neutral charge and we have opposite charges. Which of those interactions would I expect to be stronger? The opposite charges. Why would the opposite charges be stronger? Opposites attract because they're neutralizing charge. That positive-negative association is now a very strong attraction because what we're trying to do is become neutral, become unreactive. When we look at that bottom case, they are already neutral. There is no reason for that molecule to interact, which means when it gets near another molecule, it is completely indifferent, could care less. What happens in the top case? We take that negative and it sees a positive, it's going to immediately attract that positive to neutralize that charge as best it can, which means that top case is now going to be a very strong interaction. And that bottom case we would predict to be very weak. What about our new case C? You got a question? Sorry.
Yeah, so would the weaker one have more tendency to decay over time? To fall apart, possibly?
You're still associating too much with a bond. There's no bond there. It's just a weak interaction. And we'll talk about the application of where that goes in just a little bit. Okay. What would we expect for this next one? For case C?
Medium?
Should it be stronger than B?
Yes,
Why?
because it has aspects of A.
What are you going to say? It's partially charged. That partial charge wants to neutralize. It's okay. Should it be stronger than A?
No.
So here we go, this side. I already know. Why? A is fully charged. B is only partially charged. Okay? We're trying to neutralize a stronger charge in the case of A than we are in C. So if we were to go through and rank these according to strength, our strongest one is A, which is stronger than C, which is stronger than B, being our weakest. All of that work, what can we do with it? Okay, well, here's what we're going to try and do with it. Let's take a look at some example molecules. For that bottom one, those CHs, we're going to take a look at this compound. So there's our Lewis structure, or our formula CH4. For compound C, got our Lewis structure and our formula. And for compound A, it's close enough to being just the same. Bring some level of interpretation into this. The attractive force between molecules of A is very, very strong. The attractive force between molecules of B is very, very weak. What do we expect out of this? Anybody know anything about this compound, NaCl? It's known as salt. What do you know about salt? It's a solid, thank you. What do you know about H2O? It's a liquid. What do you know about CH4? It's a gas. Why is CH4 a gas? Settle down. Why is CH4 a gas? Well, keep going. What we're looking at is our different phases. What kept a solid a solid? A strong attraction between the individual molecules. How do I get a solid to turn into a liquid? What do I have to do? I have to add heat. What does that heat do? That breaks ultimately our intermolecular attractions. It adds more energy to cause it to move more. Now I'm at a liquid. How do I make a liquid a gas? I add even more heat. What's breaking in each of these cases? It's the intermolecular forces. Not the bonds, but the forces. Okay. How do we predict what these forces were? Then we had to look at the bonds, because that evaluated each of those individual molecules on their own. Okay. CH4 had nonpolar covalent bonds, which means it has necessarily extremely weak forces. So at room temperature, where I already have some ambient heat, what is that heat going to do? That's going to allow all of the forces between those molecules to now break apart, and we end up with all of those molecules as far away from each other as possible, which means we have a gas. We take a look at sodium chloride. Very strong attractive force between those molecules. So at room temperature, where there's an ambient heat, that ambient heat isn't enough to break that intermolecular attraction. So what happens? Each of those molecules is now fused to other molecules, and they don't move. What phase best represents molecules being locked next to each other? A solid. When we move to water, we now have this kind of intermediate gray area where we have some attractive force, but not a lot. What happens at the ambient temperature? Well, ambient temperature is enough to break some of those forces, not all of them. So what ends up happening? Our water molecules move around a little bit, but they're still kind of stuck. We now have a liquid. So what we can do is predict the different phases of any substance based off of understanding their bonds. Once we know the bond, we can then predict the force. Once we have the force, we can then come up with an approximation on should that be a high boiling point, low boiling point substance. We can guess at what phase we would expect to see. Okay? Questions on that? Okay. Ranking these is weak, strong, medium. It's kind of weird. Okay. If we think back to the names we gave to our bonds, we call our bonds weak, strong, medium. No, we gave them names: ionic, covalent, polar covalent. We gave some kind of name system with this. So guess what we're going to do with these new interactions? We need to give them some names. All right, so let's try and clean some of this up a little bit. And by a little bit, I'm just going to erase everything. What type of bond did we have in sodium chloride? What type of bond did we have in the other sodium chloride? What type of bond did we have in OH? Polar covalent, that's too many words. Okay. And because we actually have those linked to each other, these two things are now actually tied. Okay. So I have a north end and a south end, also known as true. How many ends are there? 2. What's the name for 2? Di. The north end of the planet is known as the North Pole. Guess what I have? A dipole, meaning 2 charges. So it's a dipole compound as opposed to calling it polar covalent. It means exactly the same thing. It just condensed the word down, made it a little bit easier to understand. Which means guess what we have in the other OH molecule? Dipole. Last one. What type of bond do we have down here? Non-polar covalent, also a very long word. Okay, so we're going to start down there, and I don't feel like writing out non-polar covalent again. Okay, we said both of those interactions were equally likely, okay, which I just lost connection. Hopefully it catches up here in a second. Okay. So now what happens? Would we predict that force to be particularly strong? Would we predict it to actually even be valuable? Would I ever expect a neutral compound to get near another neutral compound? Okay, unless I physically put them there, there's really no reason for those two particles to interact. Guess what the assumption most chemists made was at the beginning of discovering this?
It doesn't happen.
It doesn't happen. So what did we name it? Nothing. Because it didn't happen. We don't care. Okay. Guess what, though? It does happen. It does have some importance. Okay? So we took an understanding where we said that's completely irrelevant, we don't need to worry about it, and now it's turned into something that is important. With that added step, what might we do to show respect for the person or persons that discovered that this was important? Name it after them. So you get all sorts of names coming out of it. Van der Waals attractions is one name. The name I tend to go with is the London dispersion force.
Because that's shorter than
Wait for it, wait for it. London dispersion forces, which almost always gets abbreviated LDF. There we go. Now it's short. Okay. Why dispersion forces? Ultimately, what's happening within this is that we're looking at our electron clouds around each of those molecules. Those electron clouds are constantly moving. So at some given point in time, that electron cloud may be all, whoops, that's an eraser, may be all over here. If I'm looking at that molecule, what do I see? Are there electrons there? Try this again. What are the red dots supposed to represent? The nuclei of our atoms. Here's our electron cloud as we would typically expect it, all the way around it. Because our electron, what the heck just happened on my screen? Oh, that's going to be unpleasant. What happens now? What would we see? From that arrow pointing inwards, what do we see?
It would just be
Nothing? Nothing?
A big red cloud.
A big red cloud, which represented the nucleus, the protons, which are positively charged. If I came in from the other side, what am I going to see? A lot of electrons. I've now generated a partial charge because the electrons have changed their dispersion through the molecule. So depending on how electrons move around, at random points, we will find partial charges. Those partial charges are what are contributing to this interaction. Hence the term London dispersion force. It's how the electrons are dispersed. Okay. Oh, man. So just so you guys know, this is what my screen currently looks like. Everything we have written on this slide is now all over my screen. I'm not even sure what I can, oh, man, stupid. Just erase everything. OH we said was a dipole. This was also a dipole. What kind of attractive force would be attracted between those two? Being creative and original, we call that force. It's not just a dipole, because there's two of them. It is a dipole.
Oh, I was right when I said
Dipole force. The other one. This was ionic. This one was ionic. What do we call this one? We could call it ionic-ionic. That just sounds kind of moronic, huh? So we end up changing this around. We won't get into that one. We could call this as ionic-ionic. Typically, it gets referred to as ionic bonding. What is the problem with calling this interaction ionic bonding? It's not a bond. Okay? It is better referred to as, instead of ionic, as electrostatic, which is still getting at the charges behind it. Yep. So, when did we get an ionic or electrostatic force? Close. Not just that we had a metal and a nonmetal, but that we had an ionic bond and an ionic bond. Now we know we have an electrostatic force between those. How did we know that we had a dipole-dipole force?
it was a dipole bond and a dipole bond.
But we don't call our bonds dipole, we call them polar covalent and polar covalent. How do we know we have a London dispersion force?
You just do.
Non-polar covalent to non-polar covalent bonds. So by looking at the structure, we can predict something about the bonds. Once we know something about the bonds, we can predict something about the forces. Once we know the forces, we can start to predict something about the phase. All the way up. Once we're at the phase, we can now look at how different molecules react with each other within those phases. That was everything we've talked about this semester. You'll notice there is a fourth force listed on here.
But that's not a bond.
It is not a bond. That's why it's listed under the forces. You'll also notice that it is indented. Why is it indented?
Because it's different.
So we might think it's under ionic or electrostatic, but our ionic bonding happens with water. What type of bond do we have with water? It's our dipole or polar covalent bond. Okay, so why is hydrogen bonding placed indented up there when it really is an example of a dipole-dipole force?
Because science.
What was our strongest force?
So it's strong.
Ionic. What was our weakest force?
London dispersion.
London dispersion. The intermediate force was our dipole-dipole. Why is hydrogen bonding put above dipole-dipole?
Stronger.
It is a stronger force than dipole-dipoles. Why? How do we know we have hydrogen bonding?
Just do.
Number one, you have to have a hydrogen. What does that hydrogen have to be bound to?
So is this how like acids are done? Oxygen?
Has to be bonded to oxygen. How do you know oxygen? So I said water was an example of hydrogen bonding, so oxygen had better be on that list. Guess what else?
It's like hydroxide.
Fluorine and nitrogen.
So like hydroxide has a hydroxide.
We have to have a hydrogen bound to those. If we have satisfied that, then what we can do is evaluate, do we have a dipole-dipole force? So do you have a dipole-dipole and a hydrogen physically bound to oxygen, nitrogen, and fluorine? If yes, guess what the force is? Hydrogen bonding. Okay? So it is a conditional force. It has an extra rule behind it. Why is it stronger than dipole-dipole? Hydrogen is pretty much the lowest electronegativity we can get without becoming a metal. Oxygen, nitrogen, and fluorine are all the highest electronegativity we can get. Okay, so we're taking the lowest electronegativity and the highest. We're starting to approach as close as we can possibly get to the ionic bond. Okay. What we do with this is can predict our different phases. We can predict vapor pressure, viscosities, surface tension. All these amazing things come out of this based off of understanding something about the forces. Just a second. This figure shows the interplay between these. If you look at a molecule and you decide that it is a covalent bond, the covalent bond corresponds to roughly a black or purple color. Let's call it purple, because purple is a little more exciting right now. Okay. What type of force would I expect for that purple covalent bond? A purple London dispersion force. They directly tie straight across from each other. If you have a yellow polar covalent bond, what type of force would you expect? Yellow, very likely, hydrogen bonding. These are related to each other. We're taking the strongest interaction, and this is a fun one. The strongest interaction between any two elements is a covalent bond. As we progressively weaken that, we move to a polar covalent bond, to an ionic bond. If we weaken that further, it shifts from being an ionic bond to an ionic force. As I continue to weaken that attraction, it becomes hydrogen bonding. Then it becomes a dipole-dipole. And then I can look at the absolute weakest possible interaction I can get between any two atoms, London dispersion. Okay. They are all intricately tied through this spectrum of colors. Okay. One of the most confusing aspects that most students tend to trip up on when interpreting bonds and forces, particularly when we talk about the strength of an ionic bond versus a covalent bond. Okay. Almost everybody references an ionic bond being stronger than a covalent bond. And the example almost everybody goes to, sodium chloride is an ionic bond. Methane has covalent bonds. Well, ionic bonds must be a stronger force because they're a solid and methane is a gas. Right? Sounds legit. What are you comparing when you make that comparison?
Two gases together.
You're not comparing the bond strength. You're comparing
Substance strength.
the force strength. When you melt sodium chloride, you are breaking the bond between sodium and chloride. When you melt solid methane, you are breaking the force between a methane molecule and another methane molecule. You do nothing to the bond. Really cold temperatures. Okay? So what you have to realize is pretty much all of our physical properties come out of the forces. We can predict the forces by knowing what bonds we have. But our covalent bond is still stronger than an ionic bond. Okay? So, we're going to end this on a quiz. Any one of these four. This one won't be too bad. We'll pick up on doing this one too. So we officially got, I think, 5 minutes. Any one of these four, what I want you to do, take a look at the two compounds within that set. And I want you to give me the bond type, the strong or the most polar bond, well actually all the bond types. And I want you to tell me the force. Okay, the strongest force found in that compound. So list all the bond types in the compound and the strongest force for any one of those sets of two. You got your question? If you got questions, raise your hand. I'll come to you.
Oh, sorry.
all bonds within the structure and the strongest force. We can talk to people around you too. I never expect quizzes to be closed. So this theoretically from drawing Lewis structures in lab you would have picked up, but maybe you missed this.
We skipped that lab. Yeah. We did skip.
We didn't do that.
Yeah, we did that.
Cut that one
Oh,
out.
yeah, we did skip it. Yeah.
Is this the lab where you put the little models together?
Yeah, that sounds fun. Self-learning we didn't do. Screw binding proper.
Yay.
Carbon, carbon. Both of those bonds are non-polar covalent bonds,
Which means the force.
which then means what force?
LDF.
LDF forces.
Oh, I got it right.
Take a look at the next compound. What bonds are in that compound? C to H and C to C. What type of bonds do we have? Non-polar covalent, which means what force?
LDF.
LDF. What we'll pick up with on Thursday is what do we do with this? So I fully expect every single one of you to take all of those four structures out of the slides and classify, just like we did here. What are the bonds? What are the strongest forces coming from them? That's where we'll pick up.